Hi guys, this is Mrs. Gastler, and in this video we are going to talk about the conservation of linear momentum. And I wrote some things down to make this video go just a little bit faster, so if you need to pause to be able to keep up, please do. So I'm going to go through the derivation of how we know the conservation of linear momentum is true. If you don't want to write this down, it probably isn't the end of the world. It's definitely in the textbook that you have access to, and you can totally find it on the internet. And you might even be able to think it through. So if you don't write this down at all, that's really not the end of the world either. But some people really like derivations. So if you really like derivations, you may actually want to write this down. Okay. So I'm going to start up here, and I'm going to display a little bit at a time. If you have questions, stop and go find me and ask questions, okay? So conservation of momentum, we're actually talking about linear momentum right now, okay? Linear momentum means we're going in, we're actually not necessarily going in straight lines, lines, but we could be going in one or two dimensions. So maybe we're going along a line and we're confined to go along the x-axis or the y-axis or the z-axis. And maybe we're moving around in a coordinate plane, following like a line on the x and y plane, or maybe we're going in a three-dimensional coordinate system, and we've got a line in here. Those are really hard to draw actually, but 3 dimensions is hard to represent. But we're going on a line, okay? So that's going to be linear momentum. In a couple of units, we're going to talk about something called angular momentum, which is for things that are rotating, which is a little bit different than moving in a line. And we might even have something that's going in a circle, and that's not exactly angular momentum. That's really for something that's rotating. So if I spin my pen, it has angular momentum when I do that. But if I take my pen and I move it in a circle, that's something a little bit different. Okay. So we'll talk about that more later, but we're talking about linear momentum, and nobody wants to write all of that out. And so I abbreviate it CLM. Okay. Conservation of linear momentum. And so that's what I wrote at the top of the page. I'm gonna flip this over because that's going to distract me. And so what we're talking about most of the time when we have conservation of linear momentum is objects that are interacting. And maybe it's two objects that are running into each other. Maybe we have an object that is changing somehow because of another object that is doing something from some other direction. Maybe they're coming in at angles. Maybe they're starting like this and something is separating them. Either way, they're interacting in some manner, okay? And so we're going to think about the momentum that is involved and the interactions that are happening. So when objects interact, there's going to be some forces, okay? There's going to be a force on one and then a force on the other because that's what happens. That's Newton's third law, right? So I wrote here, this is the, we're talking about impulse, right? This force times time is the impulse. So we've got two objects, which means we have two of these impulses. Two forces are happening. So we have the force on B due to A, force on B due to A. That would be here. So this is the force on B due to A. And then there's a force on A due to B. Okay, so there they are. Force on B due to A times the time. That's going to change the momentum of B. So this force is going to change the momentum of B. And the force on A due to B, that's this one, that times the time that's happening, that's going to change the momentum of A. So that's all I've written here to begin with. And that's just stating what's happening, okay? Now, according to Newton's third law, those forces are equal, but in opposite directions. So there's a little negative sign right there, okay? Those forces are equal, but in opposite directions. Pretend these arrows are exactly the same length. And they happen at the same time for the same length of time, okay? So those are equal there. And so since these guys are negative and this is the same, that means that these guys are negative and the same. So that's what I wrote right there. Ta-da! Okay. Now, I've got B on one side and A on the other, and I really like A to be first, so I switched those. That's all I did. All I did here was I switched them so that A is on the left and B is on the right. Unless I have my left and right switched. Yeah, okay. All right, so now the next thing that I did was I just, I took the definition of momentum here and I replaced the P with the M and the V. Okay, so the mass isn't changing. The mass can change, you know, if I knock a piece off. In fact, that's another kind of interaction that could happen if I just have the one object A and maybe it's a bomb and it explodes, kaboom. Then I have the mass of the one object and it splits into a couple of different masses. Maybe I start with M, big M, and then it blows up into M1 and M2, you know, and so I have V1 and V2. So maybe this might look a little bit different depending on exactly what the interaction looks like. And so drawing a picture of what's happening can be so useful in figuring out what to write down for what's going on, okay? So, which we'll talk about a little bit later on here. So we've got MA and these different objects here, okay? So this is just, I haven't even done anything yet here. So I've just replaced the definition yet, okay? So now what I'm gonna do is I'm gonna expand it. So I've just left this negative here. This negative has to kind of follow us along because they're opposite directions because of that Newton's third law. So what I'm doing from this step to this step is I'm using the definition of that change. What does that change mean? Well, I've got to do the final minus the initial. So final minus initial, final minus initial, okay? For this step, the next thing I did was I distributed the negative, distribute the negative. So now the negative and a positive here so that negative moves across, okay? So I have distributed my negative, and now the only thing I need to do on this step, this is like a two-step here, okay? So what I want to do is I'm thinking about what's happening over time here. So what I'm doing is I'm going to put all of my finals on one side and all of my negatives on the other. So I'm going to move my final. So I'm adding the final to both sides. See what I did there? Add the final to both sides. And I'm adding the initial. So I've got the initial for B that I'm adding to both sides, and I'm adding the final for A to both sides. So I'm going to get rid of definitely have done, here's what I did. There we go. This is going away from that side, and this is going away from this side, so I'm going to end up with nothing but positives. That's it. So I'll have the initials on one side and the finals on the other, and these guys are going to go away. Okay. Moving stuff. That's what I did. Okay. So now when I rewrite this, I have the initial velocity of A plus the initial velocity of B is equal to the final velocity, or the final mass times velocity of A plus the final mass times velocity of B. Okay, so this is that's me finishing rearranging. Okay, and from here to the next step, I'm just showing you that, oh, look at that, it's the momentums. Okay, so I'm using the definitions again. And so I have the momentum of A plus the momentum of B, initial, both of those have I's on them, is equal to the final momentum of A plus the final momentum of B. And that is really just the total. Here's some more definitions here. Initial, the total, when you add them all up, that's the total initial. And I added all those up, that's the total final. And this is important because this, when the total initial equals the total final, that is telling me that momentum is conserved. When the total stays constant, that's what conserved means. Total stays constant. That is the definition of a conservation law. Okay. So that is how you show that momentum is conserved. Now, this right here is the most, well, it's one of the most useful ways to write the conservation of momentum, but you don't have to write it that way. You just have to make sure that all of your objects that you have before and their momentums are listed before, and all of your objects that you have after and their momentums are listed after. Okay. So let's practice. I've got a couple of examples that you might recognize the characters in our examples if you watch a lot of Nickelodeon or have ever watched Nickelodeon. Okay, so here's our first one. Two ice dancers, Tom and Anne, who have these masses right here, push off of each other. They're initially at rest. If Anne has a velocity, I wrote speed, then I changed to velocity, of positive 2.2 meters per second. How fast and which way, because we need to know that too, will Tom be moving? So let's draw a picture here. So to begin with, our ice dancers are going to be here, okay? And they're going to push off of each other. They're currently not moving, okay? Nobody's moving. And then later, they're going to be moving. And since this is a pie hair, we'll give Anne some longer hair so we can tell, and Tom can have short hair. There we go. And Anne is going to be moving in the positive direction, so that's going to be this way at 2.2 meters per second. They both have no movement, so V equals 0 over here. Anne has a mass of 65 kilograms, Tom is 80. And the question is, how fast is Tom moving? Can you tell which way Tom is going to be moving? If you picked in the negative direction, then you are on the right track. Good job. So let's see what we're going to have to write down here. So to think about the conservation of momentum, we've got two objects here. So we've got the mass of A and the velocity of A, initial, plus the mass of, let's use T for Tom. Tom and velocity of Tom, initial. And then the mass of Anne and the velocity of Anne, final, plus the mass of Anne and the, Tom, and the velocity of Tom, final. And we know pretty much all of those. Okay, so to begin with, the velocity of both of them is 0, which means this is 0 and this is 0. How convenient. So what we need is for all of this added together to be 0. This is actually a really convenient one. So if I just cover this up, this plus this has to equal 0, which means that the mass of Anne times the velocity of Anne, final, has to equal the negative of the mass of Tom times the velocity of Tom, final. Okay. So this one boils down to something easy to work with. So if I want to find the velocity of Tom, this is what I'm looking for. I just need to divide by the mass of Tom. Negative. The negative is going to end up in there. Negative mass of Tom. Okay. I should move this down so it's not so close. There we go. Okay. So the velocity of Tom final is going to be, if I can just fill in stuff now, right? All right, so the velocity of Anne is 2.2 meters per second. Anne's mass is 65 kilograms. And Tom's mass is 80 kilograms. And then there's a negative in there because the negative carried over. And so all I have to do is plug that into my calculator. So 65 times 2.2, that's 202. 65 times 2.2. There we go. Divided by 80. Tom's a lot bigger, so I'm expecting him to be moving slower. And he is, in fact, moving slower. I can't, the negative. Okay, negative 1.7. That rounds up to 9 meters per second. Okay, actually I could round that to 1.8 as well. So this is Tom's speed. Okay, so that is our first example of how you use conservation of linear momentum. Okay, so this is an example of where we have two objects that aren't moving and then one of them is. That's one of the easier situations where you start off with something that's not moving. Let's look at one example that is a little bit harder. Now we have Max and Phoebe Thunderman. See, I told you. Nickelodeon. All right, Max and Phoebe Thunderman, they're making pizza at Wong's Pizza Palace. The 0.5 kilogram pizza dough round is moving on a conveyor belt at 1 meter per second when Max drops 0.3 kilograms of cheese on it, and then Phoebe drops 0.03 kilograms of pepperoni on top. How fast should the pizza be moving now? Okay. And then we'll talk about this other question in a second. All right, so we've got a conveyor belt, okay, and then this is moving, so it has, 0.5 kilograms, and it's going 1 meter per second. And then we're going to add some cheese, that's 0.3 kilograms, and some pepperoni. Let's pretend that's pepperoni, okay? That is 0.03 kilograms, and the question is, how fast is it going now, okay? So we've got a before, which is just the mass of the dough plus the speed of the dough. It's not going to be changing direction, so I'm going to kind of leave that little arrow off the top. And that's all that we have to begin with, so that's all I'm going to write down. So I'm going to put my little equal sign here. Okay. Now afterward, everything is kind of combined. Okay, so I could write it this way. It's not, all of it's together. So I'm going to write the mass of the dough is still there, plus I've got the mass of the cheese, plus I've got the mass of the pepperoni. You can use this formula here, right? So we've got the total momentum before and the total momentum after. I can write it the way that I need to be able to think about what's happening. Okay, it doesn't always have to look like this object plus this object equals this object plus this object. I can think about what's going on and I can write it the way it makes sense. So I've got dough, cheese, and pepperoni on here. They're all moving at the same speed because they're stuck together, presumably, right? If you saw that episode, that was all over the place, but we're pretending it's not, right? Spherical chickens in a vacuum, okay? And then they've got some, we'll just call it pizza now, right? Okay. They've got some speed that they're going. Okay. So all I need to do at this point, I know these variables and this all here, and then this is what I'm looking for. And so I just need to plug in my numbers and go, right? So to solve this, I'm just going to be dividing by all that mass together, just like I did in the last one. So this one will be, let's see, this is so if I just wrote it that way first, I could write it this way, divided by all that mass, dough, cheese, pepperoni, and that's going to be the velocity of the pizza. Okay. So let's see. This was 0.5 times the 1, and then the 0.5 kilograms plus 0.3 plus 0.03. And that's going to be the velocity of my pizza. Where did my calculator go? 0.5 plus 0.3. I should know this one. That's 0.83. Okay. So 0.5 divided by 0.83 times 1 is 0.6 meters per second. Now this second question here says, in parentheses, why does this not necessarily happen? What do you think? Why does this not necessarily happen? I'll give you a hint. It's on a conveyor belt. So if this were on a skateboard, the skateboard would definitely slow down. But it's on a conveyor belt, and the conveyor belt is being forced to keep going by a motor, and so it's not necessarily going to slow down. The motor is actually going to have to work a little bit harder to keep it going at the same speed. If it weren't a very powerful motor, it actually would slow down, and that's what motors would do if it were being. If there was some computer controlling it to keep it at the same speed, the motor would have to work harder to keep it going, which is actually pretty cool. And so that's a couple of examples there. If you are working through problems on any of the practice that you have available and you get stuck and you're not sure how to do, some of these require a lot of extra thought on how you're going to set the problem up, but it's all just thinking about what momentum do I have to begin with, what momentum do I have to end with, what do I know, what do I need to know. Sometimes things fall out of the equation, so you just have to think it through. Okay, ask questions if you have any, and thanks for watching.